Let's talk about the work done by a varying force. Okay, so let's review a little bit. We've talked about the definition for work, and this is our definition of work so far. Work is equal to a force dotted with a displacement. Okay, F dot delta R. Now this is the dot product we talked about last time. Well, really what you're doing is you're saying what's the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the force and the displacement. That's our definition for work. Now remember what's happening. When you're doing work, you're transferring energy from one system into another. And we haven't really talked about kinetic energy yet. That'll be next time, next Monday. And then also gravitational potential energy. That's coming up in Chapter 8. But do know this. When you're doing work, you're taking energy, which is that ability to make changes to your environment, that weird, intangible stuff that objects have because they're either moving really fast, or they're up high in a gravity field, or they've got chemicals that want to react and give off this energy. But work is when you're transferring that energy from one system into another by applying a force, and it has to be through a displacement. Okay, so and then we also did this dot product with I, J, and K unit vectors to make sure that this weekend when you get caught up with all of those assignments, you follow that. All right, because that's what we're doing. Now, this is all fine and dandy, but I want to show you something here. We can draw a graph of force as a function of position here. And so let's say let's just write a problem. A 3 Newton force is applied through 5 meters of displacement. Okay, and we want to find how much work did we do. Well, we've done this before. Anytime you've got a quantity that's a product of two other quantities, you can graph this quantity as a function of this quantity. So now, and by the way, let's just assume that the force is in the x direction and that my starting position is 0. So, 1, 2, 3, 4, 5. Okay, and this is 1, 2, 3. This is force in newtons. So if I apply this 3 Newton force through 5 meters of displacement, I can say, well, okay, the work is equal to F dot delta R. Let's start with our most basic definition of work we have so far. And we say, okay, well, this work, let's take a look at this. This force is 3 newtons times, well, what's our delta R? Well, we're starting at the origin and we're going out to 5 meters. So that's going to be 5 meters. And we're assuming that the force and the displacement are in the same direction. So it's a cosine of 0 degrees, which is 1. And so when you do this, you get, okay, 3 times 5, that's 15. And a Newton times a meter is a joule of energy transferred. Okay, there's my answer. But why do it this way when I can spend a lot more time drawing a graph? Okay, so that's what I'm going to do. I'm going to draw a graph. So here at 0 meters, my force is 3 newtons. At 1 meter, it's still 3 newtons. Still 3 newtons. At 3 meters, 4 meters, 5 meters, still 3 newtons, constant force. Notice that this draws a rectangle. And if I look at each one of these little squares, let's look at this square right here. It has a, an area is base times height for a square. And this area is 1 meter. Let me zoom in so people in the back. So that's 1 meter, and then this height here is 1 newton. So when I multiply these together, I get 1 times 1 is 1, and a newton times a meter is a joule. So each little square under my graph represents a joule of work done by the force. And so what I can do is add up the number of squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 joules, of course. Now, we've done this before. Remember, we said the area underneath the velocity versus time graph was our change in position, our displacement. We said that the area underneath an acceleration versus time graph represented my change in velocity. Okay, now we're going to say that the area underneath a force versus position graph represents work done by the force. Now, again, this is a really profound idea. Anytime you have a quantity that is defined as the product of two other quantities, you can do this. You can graph this as a function of this, and the area underneath the graph will be this. Okay? And of course this will bring us to integral calculus. I mean, what if my force varies? What if the force, let me zoom back out then. What if you have a force that varies with position? Okay, well, like this. So here's position and here's force. Now this is very common. You can have in a machine, for example, you could have a force where there's a cam and a spring and other things going on, where the force that's being applied depends on where the object is. I mean, a bow and arrow, right? At first, when you pull the string back, it doesn't take much force, but the more you pull back on that arrow, the more force you have to apply. But of course, they have these compound bows with pulleys and all that kind of make it a little bit easier at the end. So that would be a more complicated function, but there's lots of examples where the force that's being applied by something depends on where it is. It depends on its position. So let's just make up some arbitrary force function. Might look like this. Okay. Now, how would you calculate the work done by this force? Well, what we're saying is that the work done is going to be the area underneath the graph. Okay. Now, by the way, if it's negative work, like if it was a force that was, if the position is positive, the force is negative, then, obviously it's the area under the graph. You have to kind of put under in quotes. It would be the area from the function to the horizontal axis. Now, what we have done, and we've done this before, is we break this up into rectangles. And we're going to calculate we're going to give each rectangle a width. We're going to call it delta x. And it's got a height. And that height is f of x. Now F here means force, not function. Of course, the force is a function here. But the area of this rectangle right here, if this is x, this delta x or whatever, you would say, well, that little bitty area is the force at that x times delta x. And again, we're kind of doing this, we're doing a simplified version of this. We are going to assume that the force and the displacement are all in the same direction. We're going to ignore the dot product kind of part of it for right now. We'll come back to it. And what we're going to do is we're going to add up, we're going to sum all these rectangles. And, you know, n is the number of rectangles we're going to add up. Now, of course, what we do in integral calculus is we make delta t shrink, or I'm not delta t, in this case it's delta x. We make delta x shrink to 0. And so this summation becomes an integral summation of the force. And the force has to be a function of x in order to integrate this with respect to x. And our delta x becomes a dx. Now we have to have an initial position, x initial and x final. For example, you could say how much work was done from here to here, in which case you would just, you know, calculate this area. And then, well, actually what you do is you calculate the total area and then you subtract away the stuff you don't want. You know, that's that definite integral stuff. Okay, so this is now, well, this will be my definition for work for right now. And let's see, can we get to that? Well, now this is assuming that the force is in the x direction and my displacement's in the x direction, and so we're just kind of looking in the x direction, keeping it one-dimensional for right now. Now, so this is the equation I'm really going to be using, you'll be using for the homework and so on. Now, if I wanted to generalize this to displacements that are in three-dimensional space, forces that are in three-dimensional space, you could do that. You say work is equal to the integral from r initial to r final of, you know, my force dotted with dr. Okay, this is right here the most general expression we have for work done. And what I like to do is start with the most general expression in my work. When I solve a problem, I will do this. I will start with this, and then what I do is I break it down. And I'll say, oh, okay, instead of dr, we're just dealing with the x direction. Everything's in the x direction. So I would write this down first, and then when I start solving the problem, I will recognize, hey, we're only dealing with the x direction. And when you do that, this general expression becomes this. And then I can plug in my function in dx, and I can use those integration rules to solve the problem. And that's what you're going to have to do. And they've got a couple of example problems for you to do. Now, if I look in the book, though, you don't always have to use integral calculus. Sometimes you'll get a problem like this one. This is one of the example problems where you have a force that is constant and then it decreases at a steady rate. And here it's much easier just to say, oh, the work done is just the area underneath this graph. So here's a rectangle and a triangle, so find the area of the rectangle and the triangle and add them together. That'll work. Then you don't have to, especially for those of you that are new to calculus right now, that's a good way to do it. Okay. Now we're going to look at a particular varying force that's very, very important in mechanical engineering, and that is the work done by a spring. Am I on camera? Yes, I am. So let's talk about the work done by a spring. Now, first let's figure out what the force applied by a spring is on an object, and we're going to look at a really simple diagram. Now, we talked about Hooke's law earlier but let's review it. Suppose I have a frictionless surface. Well, I'll show that by, here's a little box or crate. We love crates. And it's on wheels. And it has a certain mass. Now, when I put it on wheels, that means, hey, there's no friction in this problem. All right? Now, I'm going to say this is 0. And 0 is where the spring I'm going to put doesn't have any force acting on the object at all. The spring is relaxed. So here's a spring. Okay? And this is going to be x. This is going to be my x-axis right here. Now, if I pull this object to the right, let's pull this out to some maximum x max. Now I had to pull it, and then I'm going to release it. Now, that instant I release it, let's take a look. Let's look at the forces acting on this guy. Of course, you've got gravity, right? And of course, you've got a normal force. But these forces are not doing work in this problem because they're perpendicular to the direction of motion. They're not adding or taking away energy from my crate. But there is a force acting on it, and that's this force right here. The force, because what did I do when I pulled this thing from here? I pulled it over here. What's the spring doing? It's pulling it to the left, all right? And when I release it, this becomes a net force, doesn't it? And so this is the force of the spring. Now, what if I instead of pulling it out like this, what if I compressed it? What if I pushed it over here somewhere? Like if I pushed it right here, put the crate right here, well, what direction is the spring pushing on my crate now? To the right. So what I'm going to do is just make a statement here. This is called Hooke's law, and it works for most springs. This is not a law of nature. Okay, you can find springs that don't obey this little equation, but just to keep things simple, we're going to assume that these are Hooke's springs, or springs that obey Hooke's law, which says that the force of the spring is directly proportional to my position, or my position away from the equilibrium position. This is called the equilibrium position because at this spot, the spring applies no force at all to the crate. I'm defining the origin to be where the spring is in equilibrium position. Yes? Okay? So, now, and what we find experimentally for most springs, unless you overstretch or overcompress the spring, that the farther I pull the spring out, the greater the force. And that the force is directly proportional to how much I stretch that spring. Okay? But we need a constant of proportionality. We need what's called a spring constant. Okay. Now, I think we talked about spring constants briefly earlier. But what is a spring constant? It is a measure of how stiff the spring is. It's measured in, we're using the metric system here. It's in newtons per meter. This is a measure, okay, how many newtons of force do I need to stretch or compress this spring by 1 meter? And you might say, well, what about the spring in this ballpoint pen? I can't stretch that a meter. No, you can't. If you tried, you would snap it. But you can stretch it a centimeter, which is 0.01 meters, and you can measure the force it takes to do that, and therefore you can come up with the ratio of newtons per meter. This is just a ratio, okay, of how. So if you had like 1,000 newtons per meter, actually 1,000 newtons per meter is not that stiff of a spring, but like 20,000 newtons per meter, that's a pretty stiff spring. That'd be like the spring on your truck. If you have a truck and you have those big cantilever springs or whatever. These are pretty weak. This would probably be like, 20 newtons per meter or 30 newtons per meter, the spring in a ballpoint pen. Okay, so all we're saying is that, look, the force of a spring has to be in newtons. My position from the equilibrium is measured in meters. So this has to be newtons per meter, right, in order to have the units work out. Okay, now what direction is the force of the spring compared to my position? If I pull this in a positive direction, if x, look, here's x is 0. So x, I'm pulling it like this. What direction is the spring pulling? In the opposite direction. So if I pull this spring out in a positive direction, the spring pulls with a negative force. So you need a negative there. So the force applied by a spring is equal to, it's directly proportional to my position away from the equilibrium position. This is just a property of the spring. You could have a stiff spring or a weak spring. And this indicates the direction. So let's make these vectors. Okay. And this right here is called Hooke's law. And it really does work most of the time. For most of the springs that you're going to work with in industry, the force that you apply will be, directly proportional to the displacement away from the equilibrium position, but in the opposite direction, and times some spring constant. Okay. Well, let's graph this. This is a function. This is a function of my force as a function of position. Okay. So this is going to be the force applied by the spring on my object. And this is going to be position. This will be measured in newtons. This is in meters. Although I'm going to keep it qualitative here. I'm not going to put any numbers. And what we're going to do here, straight edge. Look, this is a straight line function. The y-intercept, or the vertical intercept, is going to be 0. When x is 0, the force is 0. We define the origin to be that, right? We define x equals 0 to be the position where the spring is relaxed. It's not applying a force to the mass at all. So this is my origin. This is the slope of the line, isn't it? At k. But it's a negative slope. That means that this is going to be some function like this. Here's my force function. This is the force the spring applies to the mass. So you might ask yourself, how much work does the spring do? Well, it's the area underneath the graph. Now let's take a look at my picture here. Let's say I'm going to push this thing back here and then hold it right here. So I'm going to hold my little massive object right here. So here's negative x maximum. This is my maximum position. I'm gonna hold it there. Okay? And then I'm gonna release it. Let go of it. What's the spring gonna do? It's going to do work. It's gonna push this crate to the right, isn't it? It's gonna push it to the right. And therefore it's going to the force of the spring is going to push it to the right. It's going to move to the right. So the force and the displacement are in the same direction. They're both the crate is moving to the right, so the displacement is to the right. It's the force, so it's going to do work. Now, how much work does it do going from here to here? This much work. So if you think of the journey, you pull this thing on here, you hold it there. Then you release it. That's when I'm starting to look at it. I release it. Boom. And what does it do? It moves to the right. It's going faster and faster and faster. The spring is transferring energy from its own compressed self into the massive object. Because when the massive object was over here, it really didn't have any energy. It wasn't moving. All the energy was in the compressed spring. When I release it, the spring pushes on it and it displaces to the right. And therefore transferring energy into the moving massive object. We call that kinetic energy. We're going to actually derive the kinetic energy next time, or on Monday. Okay? Okay, and so you say, how much work did it do? Well, it did this much work from here to here. Well, then what happens? Well, when it gets here, when you get over here, what is the spring doing now? Well, it's going to slow it down, right? It's going to take kinetic energy away from the crate. When the crate moves from here to here, think about it, it's going to slow down to a stop, isn't it? And here's, this is positive x max. The spring is going to do negative work because as this crate is displacing to the right, the displacement is to the right, but the force is to the left. When the force and displacement are in opposite directions, negative work is being done, which means that that force is trying to take energy away. Energy is being transferred out of the moving object. Energy is being, we're taking kinetic energy away from the crate and putting it back into the spring is actually what we're doing. And then what will happen? Well, it'll just oscillate back and forth. Okay, basically forever. But the point here is that the work done by the spring is equal to the area underneath the graph. Yes?
Does it go all the way to positive x max?
If it's a symmetrical spring, and we're assuming this is a very symmetrical.
So like it doesn't
This and this should be, I did draw it the same, but this x max and this x max should be the same magnitude.
It's like not losing energy theoretically?
Theoretically, if there was no friction in the system and no air resistance or anything, what we're actually doing, and you're anticipating where we're going next, the energy in the system is oscillating between being in the kinetic energy of the massive object and contained either in the compressed or the stretched spring. Okay, so we're just, the energy is oscillating. Okay, and so that's an excellent question. Okay, now what we need though right now is we need an equation that expresses the work done by a spring. And so that's what we're going to do here. We're going to, I mean, we can do it based on the triangles right here. But let's do it using, because I'm getting low on time now, let's do it based on work is equal to the integral from x initial to x final of f of x dx. Okay, I'm just going to keep everything in the x direction here. Okay, so work equals, now I'll tell you what, let's just start from the origin and go to some arbitrary value of x. So here's x, okay? And we don't have to do that. We can, but I want to start off simple. So we're going to say that our x initial is 0, and then this will be just some arbitrary value for x. Now we have a value for f of x. I mean, we have a function. We said the Hooke's law, our force is equal to negative kx. Negative kx. So this, here's this, integrated with dx. Now, this is a very simple integral. And I think all of you should be able to do it, or at least look up how to do it. I think I got a couple people that are in AMA right now. You're going to have to really review what we did 3 or 4 weeks ago. But remember the power rule here. You have negative k, that's a spring constant. This will be x squared over 2 measured from 0 to x. Okay, and so the work done to go from the equilibrium position to some arbitrary value of x is equal to, we'll plug that in, you get negative kx squared over 2 minus 0. When I plug the 0 in, the whole thing goes to 0. So the work done by a spring when you stretch or compress it is negative 1/2 kx squared. And I am troubled by this. Okay, now let's go from one position to another position. You don't have to start at the origin. You can start anywhere you want. So the work is equal to some x initial to x final position, negative kx dx. So the work is equal to negative 1/2 kx squared from x initial to x final. And so the work done by, now this is the work done by the spring. And so now I can just plug these in. Negative 1/2 k, and then I'll just do this. This is going to be x final squared minus x initial squared. Now I can just put this in there if I want and change the order if I don't want to get rid of that negative. But you know what? I'll just leave it like this. This is good enough. So this is the work done by a spring. One thing to notice here, what if x final equals x initial? It's going to be 0. So, in other words, if you finish where you start, you don't do any work at all. Now, that's a really profound idea because there are certain forces that if you end up where you started, position-wise, no work was done. And the forces that do that are called conservative forces. And those are going to be really important in about 3 or 4 weeks. Okay, we're going to talk about conservative forces, so I'm just giving you some clues. So, okay, let's just review real quick what we did. Let me zoom out. All the way. Remember, work is force dotted with displacement, but work is always represented, or can be represented by the area underneath a force versus position graph. That's the work done by the force. If you have a varying force, that's cool. Just figure out what the area is underneath that graph. It'll still work. Each little square under here represents a joule of work. So all you have to do is count the number of squares, but that's kind of tedious. So we can, if we have a function here, we can use integral calculus to determine the area underneath the graph. And one of the most important applications of a varying work done by a varying force is a spring. Remember Hooke's law, the force of a spring is negative kx. And so we can graph the force of a spring being here. Oh, one thing I didn't really mention, the slope of this line is your spring constant. Okay. And then we can use, finally we can use that integral definition of work to determine the work done by a spring. Okay. I think that should be enough to get you started.